Okay, it's time to start, so I will. So this is where we ended up on Friday, talking about what voltage versus composition curves look like from our lattice gas model. And we asked the question, where might an attractive interaction between intercalated lithium atoms come from, like the red curve? And also, what does it mean for a voltage versus composition curve to go up with discharge? And we'll find out that this is unphysical and does not actually occur in a minute. But first, let's just figure out where an attractive interaction can come from. So I want to use my document camera to show you that. So let me stop sharing. Okay, so you should see my document camera now.
Yep.
Is that true? Okay, thank you. So let's talk about where an attractive interaction may come from. So imagine you have a layered host like this. Every single layered host that exists, when you put the first intercalent atoms inside, the layers move apart just from the physical size of the intercalent. That's true for every single one. There's no layered systems that contract when you put intercalate inside. So if you think about what happens, you have a situation like this, where the intercalent is in there, and it kind of deforms the layers around locally. So you made a bigger layer spacing here. And there's some strain energy required to do that. You have to actually strain the host lattice. So the next atom that comes along, it could say, look, if I go nearby, the lattice is already opened up for me. Okay. So this is called a strain mediated attractive interaction. Now, it can also take place in non-layered hosts. If you think about a situation where you have, like LiFePO4, where you have tunnels. I mean, I'm drawing it in a silly way, but the idea is if you put a lithium atom within a tunnel, again, it causes a local expansion. Tunnel's going to deform. And then you have a choice to put a lithium atom far away in the tunnel, way down here where it's not expanded, it has to do the work to do the expansion, or put it nearby where it's already expanded. So, and as we'll see, you know, LiFePO4 is a situation where the voltage curve is two-phase. It means all you ever find is completely empty or completely full. You never find, you know, a situation in LiFePO4 at room temperature where the lithium is uniformly spread in the tunnel. It always clustered together or nothing. And you could argue that maybe that comes about from this strain-mediated attractive interaction. So it's one source of a way that you can have attraction between intercalated species. Okay, any questions about that before I go back to the notes? Okay, hearing none, I'll go back to the notes. All right, so now the question for us to figure out is what happens in the case where one has this attractive interaction, the red curve. Okay, so this is where lithium atoms attract one another. Well, any system will attempt to minimize its free energy at all times. So if you spread the lithium randomly on the sites, which is the assumption in mean field theory, you'll follow this red curve. This is what the free energy does. Now imagine that instead of doing this, you say, well, I'm going to make up a system at 50% occupation by half of the material with no lithium and the other half full of lithium. So it's just like I'm talking about. The lithium will just cluster all together in one spot. Well, then the free energy of the material at 50% full would be made up of the average of the free energy of the empty and full. It lies along the straight line between the endpoints, and it's lower than the free energy of the random mixture. So I'll show you what I mean. Okay, so let's go back to the document camera. So if the free energy is concave down versus X from 0 to 1, say it looks like this. Well, what the system will do is, by forming a two-phase mixture where the compositions are given by the endpoints, the free energy will lie along that dashed line. Okay. So let's look at what happens when the interaction is 0. There's no interaction between the lithiums at all. They're just randomly distributed and very happy to be so. That gives you this voltage curve in blue. Or if the interaction energy is minus 0.1 EV per atom, or minus 0.2. Well, at minus 0.1, if you look at the curve incredibly closely, you'll see the voltage versus composition is always going down. It doesn't go up again. It's, if you look at it carefully, it's pretty darn flat, but it's always decreasing there. Whereas if you look at the red curve, you can see that it goes up. It's given by the slope of the free energy curve, but here we subtracted off a term just to make this visible on the screen. So what happens instead is shown on the next slide. So instead of the voltage going upward, here we're just looking at some values of the attractive interaction very near to the critical point where you get phase separation. If you were to draw the line on the graphs below, which goes from, you draw the tangent to this point and that point, you'll get a free energy curve that's slightly lower than the green curve. And that, of course, would have a constant slope. A constant slope means a constant voltage, and the voltage composition follows the black dashed line as you see here. So you never have a situation where the voltage goes up with concentration. It never happens. Instead, you'll follow this dashed line. And this dashed line is called the Maxwell construction. And it's clear that you'll get into this situation once the voltage composition curve becomes perfectly flat. So with gamma u equals minus 0.1, if you take dx dv, the derivative of this curve, excuse me, of the black curve, and I guess I'm taking negative dx dv because x increases when the voltage goes down, so this is actually negative. So this should be plotted as minus dx dv up here. But you can see there's a very, very sharp peak around the middle at 50% filling. And once this peak goes to infinity, that's when this curve becomes perfectly flat. And at that point, for values of gamma u that are more negative than that, you will get this phase separation. So what it means is you follow this red curve. All the lithium is randomly distributed on all the sites, all this random. You get to here, and then as you move across this black dashed line, the material is made up of one phase with this composition around 0.3 lithium, and another fraction of the material is made up with this phase of about 0.7 lithium. If you were in the middle, you'd have 50% of the sample with 0.3 lithium and 50% of the sample with 0.7 lithium. And then when you go beyond this area, the lithium's randomly distributed in all the sites again. And similarly for the green curve, except the endpoints are about 0.2 lithium and 0.8 lithium in that case. So this Maxwell construction is an equal area construction. So it means if you take the area between the green curve and the black dash curve, you can see the way my mouse is moving, the area of that little spot, that should be equal to the area of this spot between the green curve and the black dash curve. It means I positioned the black dash curve a little bit too low because these areas are not quite exactly the same. The black dash curve should be moved up just a touch. So that's how you know where to position the black dash curve. You plot the expression for voltage versus composition from our lecture last day. You see that the voltage goes up with composition. You say that's unphysical, it can't happen. And you draw the equal area construction, the Maxwell construction here, to figure out where the endpoints of the phase separation are. Okay, any questions about that?
You have no messages.
Okay, no questions, eh?
Hi, Jeff.
Yeah.
So you said the case where the voltage goes up is unphysical. Just to clarify, so the means like in actual conditions, like in the green curve. So the actual chemical cell, this they will not show up as a first down and then up, right? It will just show as a flat line. Is this the point you're trying to convey when there's a?
Yes.
See.
It will follow this point and come to the black dash curve and follow the black dash line and then back to the green line again.
So this explains why when we see these flight lines, normally means there are phase separation occurred in the electrochemical reaction. Okay, thank you.
Correct. Yeah. So like LFP is doing this all the time.
Okay, thank you, Jeff.
Any more questions? Okay, hearing none, we'll go on. All right, so now I want to talk about a real system, MO6SE8. So I talked about the structure of this in the early lectures. It has MO6SE8 clusters separated by about 7 angstroms or so. And in the range between 0 and 1, x equals 0 and 1, there's 1 lithium per MO6SE8 unit. They're basically on a simple cubic lattice, the lithiums, with a separation of 6.7 angstroms, so they're very far apart. And if you look at this first part of the discharge curve, it has a shape a lot like this black curve. Okay. So we're just going to talk about lithium filling this set of sites on this simple cubic lattice with a lattice spacing of about 7 angstroms. So sure enough, if you do incredible careful measurements, which were made on the black data points, and then you fit to the theory that we've just developed with an attractive interaction of minus 0.0904 electron volts, it fits really well, incredibly well. And this is published in this particular paper. So I'll tell you a story with Michael Wardis. So Michael Wardis, a very famous statistical mechanics guy, spent a lot of time on lattice gas models and models for magnetic systems. Anyway, I gave a lecture at Simon Fraser about this particular experiment and some more stuff coming up in a minute. And Michael Wardis was in the audience. He said, you know, Jeff, I get extremely nervous when mean field theory works because the assumptions that it makes, the atoms remain random in spite of the interactions, are just so crude that it's incredible that it could ever work. So one has to wonder, why does mean field theory work in this case when it doesn't work very well in many other cases? So let's talk about that. So this here is another paper from another set of figures from the same paper. And let's take a look at it. So figure 3 shows this dx dv plotted versus the composition at different temperatures. And the dots here are the measurements, and the solid lines are the predictions of the theory. The simple theory expression that I gave you last day, I'll write it down in a minute again, just to show you that it is temperature dependent. And these were all made for a value of U equals minus 0.0904 EV. And they predict the temperature variation perfectly, which is quite nice. Over on the right-hand side, the solid curves here are the predictions of the mean field theory. Okay, so this solid curve labeled 28 degrees centigrade is the same as the solid curve over here. So what are the data points? The data points are Monte Carlo simulations of what would happen if you had near neighbor interactions between lithium atoms in the lattice of minus 0.0904 eV. So where the interactions only take place between lithium atoms on near neighbors. Now you might be thinking, wait a minute, that's what we assumed over on the left side. We assumed that the interactions were on near neighbors. But actually, it's not what we assumed. And I'll explain why now. Okay, so the point is that mean field theory works for some reason. And mean field theory, although we said, okay, we're going to take near neighbors and second near neighbors interactions, all of this, what actually are we doing in the approximation? Because when you do near neighbor interactions exactly with Monte Carlo, it doesn't work. It doesn't match the data. The data matches mean field theory, but mean field theory doesn't match Monte Carlo. So what's going on here? Why does this work? What's happening? So I'll spend a few moments on the document camera about that. Okay, you should see the document camera again. Is that true?
Yep.
Okay, good. So I'm just drawing a little bit of a lattice for us to think about. Okay. So when we put a lithium atom here, and then we're wondering about the internal energy of this lattice, we say it's the sum 1/2 over the sum sites I and j, uij, xi, xj. This is trying to add up the interaction energies between lithium atoms on site I and j, depending on if the site I is occupied and site j is occupied. So for this case, this site is occupied and all the others are not. And then when we make the mean field approximation, we just say, okay, look, the average occupation of this site is X, and the average occupation of all the other sites is also equal to the average occupation, it's also X. We basically said we can't distinguish where the lithium is anymore because it could be over here. We just take 6. We just say there's 6 near neighbors, but whether they're full or empty, we can't tell because we're just saying everything is equal to the average. So what we're basically saying in mean field theory is the interaction is infinite ranged. We can't tell where the lithium is, really. We just know it's somewhere in here. But as long as there's lithium on the lattice, we pick up. We say it's gamma 1, U1, X squared. That's what we say the near neighbor interaction is in mean field theory. But because we assume every site is randomly filled, we don't know where the lithium is. As long as it's in the lattice, we pick up this term. All right? So it's as if the mean field interaction is infinite ranged. And that's very different than Monte Carlo. In Monte Carlo, you only pick up the interaction when the lithium is really there. So this may seem like a detail, but it's not. So what could be the physical origin of a very long-ranged attractive interaction? What is the physical origin of this almost infinite ranged attractive interaction? Well, does anybody have any idea how to get a very long-ranged attractive interaction?
It's not gravity, is it?
No, it's not gravity.
Okay.
Jeff, does this have to do with the band structure of the solid? The band structure, because it forms a band that gives the attractive interaction.
No.
Okay.
So I'll give you guys a clue. Oh, somebody's going to say something. Go ahead.
Yes, sorry, I was just saying that can we extend the strain-mediated attractive interaction over the whole layer? So can that result in an infinite ranged interaction?
That's exactly right. It's coming from the strain-mediated attractive interaction. And the strain-mediated attractive interaction is not infinitely ranged, but it's very long, because when you strain the lattice, that strain is felt over a fair distance, many lattice constants. Let me just share my screen with you for a minute. Where is my screen? Okay, so you should be able to see my screen again. We'll just go to the next slide. Here we go. Look at this. This shows you the lattice constant. So again, it's basically a simple cube that the lithium atoms sit on. It's not quite a perfect cube. A perfect cube would have a rhombohedral angle of 90 degrees, but you can see it's close to 90. And sure enough, the lattice expands as you put the lithium in. So because of that, the lithium prefers to be close together, but the expansion's not enormously huge. So the strain-mediated attractive interaction is relatively small, and it's negative, it's attractive. Okay, so now there's another problem. The other problem is, what about the Coulomb repulsion? You have these lithium atoms that you put in there. Why aren't they feeling a repulsion from the Coulomb force?
Is it because this structure happens to be special in this range of x from 0 to 1 because there are such large holes for lithium and you can put 4 lithiums into it? This might not, would this trend still hold for other types of structures where the lithiums are closer together?
The main point that you're making is the lithiums are far apart. The near neighbor distance is 6.6 angstroms. In addition, this material is superconducting. So the density of free electrons is incredibly high. So the screening is really, really good. So the Coulomb interaction is incredibly small. So it's just a fluke, really, that you end up in a situation where you have a very long range interaction, which can be well treated by mean field theory, and no appreciable near neighbor repulsive interactions due to Coulomb. So it's pretty cool. You know, McKinnon's thesis does all this work back in 1979 or 1980 with no model system that it could describe. And then this system came along later and turns out to describe it really well. Okay, so let's look at one more thing now. Yeah. So mean field theory with attractive interactions predicts phase separation at lower temperatures. I'll explain what that means in a minute. Go back to page 11, page 8, and explore the phase diagram. We'll do that now on my document camera, and we'll calculate the phase diagram and calculate what's called the critical temperature.
Hey, Jeff,
Yeah.
quick question. So when you say mean field theory with attractive interaction predicts phase separation, so you've sort of made that conclusion based on the fact that the voltage curve wasn't physical, but could there be any other explanation for this? Or I guess I don't understand how we made the jump from a curve that's not physical to this phase separation mechanism.
Yeah. Let's go back to the document camera for a minute. Okay, I think you can see the document camera again, right?
Yep.
Okay, so if you plot the free energy versus X, the derivative of the free energy with respect to X is the chemical potential. And minus the chemical potential is the voltage. Okay, so this is a curve with a ever steepening slope. So the slope is negative and getting more and more negative. So that means the chemical potential is getting more and more negative. So the voltage is getting more and more positive, right? So if you plotted the voltage curve for that situation, I don't know where I am on my chart. Uh-oh. So you plot the voltage versus composition curve for the solid line, the voltage will go up for the solid line. But the point is, look, see this dash curve? At every point, the free energy, if you follow the dash curve, which is the phase separated case, it's lower. The free energy is lower. And what's the slope of this dash curve? Well, it's this. And if you go through all the math carefully, you'll find out these two areas are equal. So the phase separation comes about because you can minimize the free energy by separating into two phases, compared to leaving the lithium random. Is that helpful?
Yeah, thank you.
Okay, cool. Okay, so now while we're on the document camera, we may as well stay here for a minute. Okay, so I showed you last day that the differential capacity, and I didn't give you the magnitude of it, but I'm giving you the magnitude of it now because the quantity itself is a negative number and I want a positive number. It's 1 over gamma U over the electron charge plus KT over E over X times 1 minus X. That's what the differential capacity is. Now, when we talked about these voltage composition curves a minute ago, we learned that once the voltage versus composition becomes perfectly flat, that's when phase separation will start to occur. And if you look at what dx dv does, versus x, if you have an attractive interaction where u is negative, this term on this side is a positive number, has to be, x is between 0 and 1. There'll be some value of temperature where this denominator becomes 0. And where that happens, dx dv will go to infinity. So what will happen is you'll get, if you can plot these curves, they'll kind of look like this. This will be low temperature. And then as the temperature gets higher, wait a minute, this is high temperature, sorry. And then as the temperature gets lower, this will sharpen up. And eventually, it will just go right to infinity. To infinity. At some value of temperature. And we can figure out what that value of temperature is by asking when is the denominator equal to 0. Okay, so when does gamma u over E equal KT over E over X times 1 minus X? I guess we want the sum of these, sorry, to be 0. So we just solve for this. So these E's cancel out everywhere. And you get minus gamma u equals KT over X times 1 minus X. We know the maximum is at 50%. We've seen that. The peak in dx dv is at x equals 0.5. So that means the smallest the right-hand side can be is when x equals 0.5. So you put in x equals 0.5 in here, and you get minus gamma u equals KT over 0.5, 0.25, sorry, when you take 0.5 squared, and you get minus gamma u equals 4 times KT. So minus gamma u over KT equals 4 is the critical point. So let me try to show you what this means with a graph, all right? So unfortunately, I need to go to another page. So the idea is, if you were to plot a phase diagram, so here you have X, and here you have temperature. And at very high temperature, the lithiums are all random on the lattice. But as you lower the temperature, eventually that numerator in dx, the denominator in dxdv goes to 0. And at this point right here, when kT over gamma u equals 1/4, and at x equals 0.5, you'll start to get phase separation as you cool down. And then, if the temperature goes lower, you'll find that there's a coexistence between two phases whose compositions are given by that Maxwell construction that we talked about. So if you make a sample with x equal 0.5 and you cool it into the two-phase region, it should separate into two phases whose composition are different. And the lower you cool, the more different their composition should be. So I'll give you a homework problem where you can work out this phase diagram for yourselves. I'm just sketching it here. But the point of this is, in our consideration of the real system, we were doing experiments at temperatures above the phase separation. And what would be the value of the critical point when minus gamma u over kT equals 4? So we learned that u was equal to minus 0.0904 eV. And if you solve this for the temperature, you get T equals 260 Kelvin, or minus 13 degrees C. And that's fully within the experimental range. So if all of this is right, it means if you take this sample with lithium 0.5 MO6 Se8, prepare a sample of that and cool it down below minus 13 degrees C, you should see it separate into two phases. So let's see if that's true. So how are you going to do the experiments? Firstly, you're going to use X-ray diffraction. And the key is that the lattice constant depends on the composition. So if phase separation takes place, a single X-ray diffraction peak at 50% should split into two, corresponding to the two coexisting phases. So let's see the experiment. So this that you see here is the raw data. And at 293 degrees, which is 20 degrees C, you see this funny shaped peak. Now, people that know X-ray diffraction know that the X-ray diffraction machines that we use have two wavelengths that are very close together, and one wavelength has twice the intensity of the other. So if you take this peak and you deconvolute it to take out the fact that the X-ray source has two peaks, you get a single peak in the middle. So this is the deconvoluted spectrum up here at the top. And then as you cool, the pattern changes dramatically. And down by 212 degrees Kelvin, you know, is that 242? No, 242 Kelvin, sorry. You can clearly see that there's two peaks, even though they each have two parts. They're clearly seen. But if you do the deconvolution, you see this beautiful splitting into two phases, and the peaks get farther and farther apart the more you cool. That's because the lattice constants between the two phases are more different because their lithium contents are more different. So this was really the confirmation that for this material, the mean field theory really worked. Okay, so why does the mean field theory work so well? We talked about the attractive elastic interaction. Why does this matter? The same type of thing happens in lithium iron phosphate. Here, if you look at the phase diagram of lithium iron phosphate, it's very complicated, okay? It's much more complicated than the mean field theory phase diagram. So this bottom panel C, it's almost like the phase diagram I sketched. It's a bit distorted, but it shows that at high temperature you have lithium everywhere, and then when you go down in temperature you get phase separation to this H and T phase, which I don't know why they call them H and T. These are very fancy calculations with density functional theory done by Gerd Cedar and his company and his people. And anyway, they end up with a more fancy model, getting a phase diagram that looks like this. At only below 400 Kelvin do you get phase separation into two phases. And if you did experiments at 500 Kelvin, you would see one two-phase region, and then a region where the lithiums are uniformly distributed everywhere randomly, and then another two-phase region. And then you can see experiment up here. So there's experiment by two different groups where they plot these phase boundaries. They don't look like the theory at all, but they do show this very strange behavior where there's first one two-phase region and then a second one. And only when you go down to low temperature do you get two phases across the whole situation. So this two-phase behavior is observed in real life. In MO6 Se8, it's the most simplest case imaginable, described by mean field theory. Okay, so we're at a good place to stop for next day. So we've spent a lot of time talking about attractive interactions, which can come from this strain-mediated phenomenon. And once the lithium atoms get close together, they really start repelling one another by the Coulomb interaction, screen-Coulomb interaction. And what happens then is usually the atoms don't remain randomly positioned in spite of the interaction anymore. So mean field theory is usually very crappy to describe cases where you have a strong repulsive interaction. But there are some exceptions. And this is one here where you talk about what's called cubic titanium sulfide. Okay, so I haven't told you what cubic titanium sulfide is yet, I don't think. But in that case, the mean field theory in blue and the data in black match really well. But what I'll do next day is talk about what we do when the atoms do not remain randomly positioned in spite of the interaction. We have to go beyond mean field theory, and how do we deal with that? And I won't make it, it'll be very accessible. We're not going to do anything fancy. We're just going to think and see what the consequences of thinking lead to. Okay. All right, so are there any questions on this mean field theory stuff? I'll give you a homework that will help you understand it better. And you can think about it between now and Wednesday if you have any more questions about it. I'll scan my handwritten notes and send them out, even though they're sort of semi-useless, but anyway, I'll still do it. Okay, any questions? I don't hear any. I guess we're done.